We are continuing with Unit 7 today, applications of the integral, and today we are looking at slope fields, which is lesson 3. So students will be able to find slope patterns of given differential equations at specific points. Now, before we get into that and what a slope field looks like, let's just remember how to graph lines. I know that's been a long time ago. This is an Algebra 1 concept. So number 1, y equals x. What is the slope of that line? Don't forget that it's 1. Whoops, my pen's a little big. 1 over 1 in the front. This is your 1. So you're going up 1, right 1 to draw your slope. Up 1, right 1, up 1, right 1. Okay, so that's a slope of 1. Now for y equals 2x, remember your slope is 2, so you go up 2, right 1. Up 2, right 1. Okay, that's what my slope looks like. For number 3, 5x, that one's kind of steep. So I start at the origin and I go up 5, right 1. And for number 4, we'll just hop over to the other graph. 1/2 x means I go up 1, right 2, up 1, right 2, up 1, right 2. Okay. And then finally for number 5, y equals negative x, don't forget that we go down and to the right. So this is just to give you an idea of, what do slopes look like comparatively? What does a slope of 5 look like compared to a slope of 2, or a slope of 1/2 compared to a slope of 1? The boxes here aren't quite square. They got a little stretched out. So just keep in mind, excuse me, that they should be scrunched up a little bit. Slope fields provide a way to visualize a family of solutions of differential equations. So when we were solving differential equations that had the plus c, a slope field is actually the graph of all possibilities of c. So what do I mean by that? Let's jump right in. Create a slope field for each of the following. dy dx equals 2. Well, remind yourself, what is dy over dx? dy over dx is the slope. So I am looking at a slope of 2. And what I need to do is draw a slope of 2 at every single one of those points indicated. So my slope of 2, just as a reminder, maybe up 2, right 1 should be about that steep. Slope of 2, slope of 2, slope of 2. And you want to make sure you hit all of these points. Now, it's important that you get them all. But it's important that you have a difference between a slope of 2 and a slope of 1/2. They need to look different. I'm trying to teach graphing lines to my Algebra 1 class right now. And so some students are doing a great job. They're counting up 2, right 1, up 2, right 1. Some are just throwing in a random diagonal line. A random diagonal line is not going to cut it. You have to be able to show the difference in the slopes. And yes, I've seen these on free response questions. So be prepared for these, and you could have to draw them. Now, let's talk about what we learned yesterday. If dy dx is equal to 2, if I separate that dx over that differential, so dy equals 2 dx, and integrate both sides, y is equal to 2x plus c. What is that? That's a line. It's a line with a slope of 2 and a y-intercept of c. So this slope field here represents all lines, no matter what the y-intercept is, all lines with a slope of 2. So that one's pretty straightforward. Oh, and the second part, graph the solution that satisfies the condition f of 0 equals 1. Remember, this notation is the ordered pair 0, 1. So you go to the point 0, 1, which is right 0, up 1, and you want to draw or graph that solution. So you follow the slope line, the slope field, and you draw in that line. Now my slope of 2 should probably be a little bit steeper than I drew it. That's looking like a slope of 1 to me. But that's what you do. You find the point that indicated and sketch in the rest. The slope fields will show you where to go. Example 2, this one's a little bit different. dy dx is equal to x plus 1. So in this case, we have to take into account the x coordinate. What do I mean by that? Let's start over here. The coordinates at this point are 2, 2. So dy dx is equal to, well, my x coordinate is 2, 2 plus 1, which is 3. So I have a slope of 3 right here. Now, this has an x coordinate of 2 as well. And in fact, everything here vertically has a slope of 2. So all of the, or excuse me, an x coordinate of 2. So all of these have a slope of 3. Now, if I come over here to the left one column, all of these have an x coordinate of 1. So 1 plus 1 gives me a slope of 2. So it's not quite as steep as the slopes that I just drew. All right. Everything here, switch colors back, has a slope, or excuse me, an x coordinate of 0. So 0 plus 1 gives me a slope of 1. So all of these have a slope of 1. And just keep going like that. Over here we have x equals -1. So -1 plus 1 is 0. All these are horizontal. These are all horizontal slopes. And to the left, we have x equals -2. So -2 plus 1 is -1. So these all have a slope at -1. So what shape do you think this might be? If I'm looking at the slope field, what shape would sit in there nicely? It's actually going to be a parabola. Now, sometimes we can solve these for the original equation. Sometimes we can't, but let's check this one out. This is kind of extra. The problem didn't ask us to do this. This is extra. So dy over dx equals x plus 1. If I separate the differentials, x plus 1 dx, if I integrate both sides, y is equal to x squared over 2 plus x plus c. That's a parabola. That's absolutely a parabola. It's shifted left 1, but we have a parabola. All right, cool. So again, this over here is extra. Sometimes you have to do that. Sometimes you don't. Sometimes you can't. Example 3, dy dx equals 2y. All right, so example 3, dy dx equals 2y. So let's look at this one. Let's switch up our colors here. Too many choices this morning. Let's go teal. So dy dx equals 2y. So again, let's just choose this point on the top right, 2, 2. So this time my y value is 2. So I have 2 times 2, which is 4. So this should be fairly steep. Now, instead of going vertically with the same slopes, across horizontally, all of these have a y value of 2. So all of these have a slope of 4. Now, a slope of 4 should look different than a slope of 3, which should look different than a slope of 2. Once you get past about 3 or 4, they all start to look fairly vertical. And by the way, you can have vertical lines in slope fields. Along this line, y is equal to 1. So 2 times 1 is 2. So these are all slopes of 2. Good. And then if we keep going here, down here, y is equal to 0. So 2 times 0 is 0. These are all horizontal. Okay. And then if we look here, y is equal to -1. So -1 times 2 is -2. So now these are going down. They take some getting used to. They're a little weird. And especially those of us who are used to that very precise graphing in Algebra 1, these feel a little haphazard. They're not, but they feel a little haphazard. And then finally, y equals -2. So 2 times -2 is -4. So these go down even steeper. Now, that's what the slope field looks like. Again, this is extra. This isn't being asked in the problem at all. But can we separate this? Let's check it out. So dy over dx is equal to 2y. So I'm going to say dy equals 2y dx. I'm going to divide both sides by y. So dy over y is equal to 2 dx. Now I'm going to integrate both sides. The left-hand side is the natural log of y is equal to 2x plus c. If I solve for y, I'm going to take e on both sides. So e is equal, no, how about y is equal to e to the 2x plus c. And we talked about that plus c yesterday, that y is equal to c e to the 2x. That's that PERT formula. That's exponential growth. So can you imagine an exponential growth curve in here? It's possible. So say it looks like this. Yeah, exponential growth, it's there. So those parent functions, those actual functions sit nicely in those slope fields is my point. Now, example 4. So you've mastered an x equation, you've mastered a y equation. What happens when we put them both in here? This can be a little bit tricky. In fact, I'm gonna have to pause my video and come back to this one, I think. So we'll be back. All right, so we've tackled the slope fields where you have just one x variable or just one y variable. So what happens when you have an x plus a y? Well, you have to take into account both coordinates. So if I look at this one, that 0.22 that we've been starting with, my slope is 2 plus 2, which is 4. So this is going to have a slope of 4. This coordinate over here is the 0.21. So 2 plus 1 is a slope of 3. So it's a little less steep. Down here, we have the 0.20. So 2 plus 0 gives me a slope of 2. Should look like that. Down here, I have 2, -1. So 2 plus -1 is a slope of 1. And over here, I have 2, -2. When I add those together, I have a slope of 0. So 0, 1, 2, 3, and 4. Now, it gets a little clunky if you put all the coordinates in there. So you want to try to kind of do this with mental math the best that you can. And then pick a row or a column to work through. So this is the 0.12. So I've got a slope of 3. This is the 0.11. So if I add those together, I have a slope of 2. This is the 0.10. No, yes, 10. So I have a slope of 1. This is the 0.1, -1. So I have a slope of 0. And down here, I'm at the 0.1, -2. So my slope is -1. Kind of crazy. All right, so I'm going to do another color here. Up here, we're at 0, 2. So I have a slope of 2. 0, 1, I have a slope of 1. 0, 0, I have a slope of 0. Over here, 0, -1, I have a slope of -1. 0, -2, so I have a slope of -2. I know that this one looks a little crazy. Wait till you get all the points in here. Over here, I'm at -1, 2. So this is a slope of 1. This is -1, 1. So I have a slope of 0. This is a slope of -1, 0. So here's my slope of -1. -1, -1 gives me a slope of -2. This is a slope of -3. And let's do one more. -2, -2, here's my slope of 0. -2, 1 is a slope of -1. This one over here gives me a slope of -2, -3, and -4. So again, those 3s and 4s start to look vertical. So this time there is a pattern, but instead of it being vertical, like it was in example 2, or horizontal, like it was in example 3, this time along the diagonal, we have matching slopes. So there's a slope of -1, there's my slope of 0, there's my slope of 1. So on this picture especially, I hope you can see how important it is that you can tell the difference between slopes. The slope of 2 needs to look different than a slope of 3. A slope of 3 needs to look different than a slope of -3. Obviously, the negatives are a big deal. Those zeros are really important, and those slopes of positive and -1. Now, in the last couple examples, I had taken our differential equation dy dx is equal to x plus y, and I was able to separate the variables and integrate. I can't do this on that. I can't do that on this one. You can't subtract the y and multiply by the x. You kind of wind up in this loop that doesn't stop. So dy would be x plus y dx, and then students say, oh, you subtract the y, but you can't separate them. So this is x dx plus y dx. If you subtract the y dx, then you have a dx on the left again. You can't do it. This one's non-separable. And the way that you can tell is if you have addition or subtraction, you can't separate those. If you have multiplication and division, you can separate, but the addition and subtraction, you can't. So I can't actually solve for my general solution on this one. The best I have is a picture of it, which is my slope field. Example 5, this is the other one type that you might see. Match the slope field with the differential equation. We got some extras in here. If I'm looking at example 5, that first graph, going up and down and up and down, I would pick a point and test it out. So if I look at dy dx is equal to x, so maybe we're at the point, and these kind of slope fields, this is what there's a program your graphing calculator can download online, and this is the type of graph that it will result in. If we're at the point over here, this looks like 0, 3 to me, and I try the point 0, 3, looks like I should have a slope of 0. So let's try this out. So sine of 0 is 0. So dy dx sine of 0. Well, that's 0, so that works, but you might have more than one answer. So dy dx, if I say 2 minus 3, that would be a slope of -1. Does this look like a slope of -1 up here? No, it doesn't, so I don't think that one's it. This one could work. If I say x minus y, so this would be 0 minus 3, gives me a slope of -3. Does this look like a slope of -3? Nope. And dy dx equals x, so dy dx would be equal to 0. Ah, that one works as well. So you have 2 points that work for that 0, 3 that we tried. So now you have to try another point. You might be able to tell if we integrate sine, what do we get? Negative cosine. If we integrate dy dx over here, x, you're going to have x squared over 2 plus c. So this is a negative cosine curve. This is a parabola. Which one fits in that first slope field? That's the negative cosine. So in this case, I could solve for my original equation, but what else you would do is you try another point. So here's, get off the y-axis. Why don't we come over here to the x-axis? Let's choose 2, 0. If I put 2, 0 in here, my slope would be 2. That actually looks like it works too, though, doesn't it? Sine of 2 is some value over here. How about this point over here? It's like 5 or something. Does this look like a slope of 5? No. So this one doesn't work. The x doesn't work. So the first one is absolutely dy dx equals sine of x. All right, let's get rid of all this other stuff. Now, some students can look at these right away and they just see the connection. Usually my visual learners do a good job with that. But some of us don't, and that's okay. You just have to practice a little bit more. So let's choose a point. Let's choose, I don't know, I'm kind of digging the origin here. 0, 0. So we've already established that sine of x was used. For the second one, dy dx equals 2 minus y, so it'd be 2 minus 0. Does that look like a slope of 2 at the origin? Nope. If I say x minus y, 0 minus 0 would be 0, that could be it. Or dy dx could be 0. That could be it. So again, I've got 2 possibilities. So you want to try another one. So I'm over here at the point 0, 2. So this would be 0 minus 2. Looks like a -2. Yeah, that's pretty believable. What about your x coordinate of just 0? Well, that's not a slope of 0. So it's definitely not x. It's this one. And maybe you could tell that it was x minus y because of that last example we did. If you have the x and the y variable in there, you get the patterns on the diagonal as opposed to vertically or horizontally. So with this one just being x, you would have matching slopes vertically. So I like slope fields. I think they're kind of fun. They're a little bit different. They do take some practice. And if you're looking at that kind of person that likes to have an exact answer all the time, these might make you a little bit uncomfortable, but sketch them in the best that you can. All right, good luck and let me know if you have questions.